So del operator is very, very important. That's why it's written in, I should have written in red, but that's okay. Okay, now what does an operator do in math? I should rephrase that. What can an operator do in math? It operates on a function and changes it somehow. Remember last time we were talking about vectors? What were the three things that we said vectors could do? Not the triple products, but plain vectors. There were three things that vectors could do. You could multiplication of a vector with a scalar. You could do a dot product, and you could also do a cross product, right? Okay, so this is an operator. What are the three things do you think it can do? You could operate it on a scalar. You could dot it with a vector, or you could cross it with a vector. Anything new so far? No? Seriously, we never do anything new. So this is what we're going to do now. We are going to define this del operator to do three things. We are going to operate it on a scalar. We can make it operate on a vector where it can dot. I should call it dot product. Or it can operate on a vector, but it can cross product it. Now here's something very interesting. When this del operator operates on a scalar, we call it the gradient. So how do I write that? A del operator operating on a scalar, I think Griffith called it T, will be called a gradient. When this del operator operates on a vector as a dot product, let me call it E.
Delhi.
Delhi, yeah. Oh yeah, that's funny. This is called a divergence. And when this vector cross product exists, it is called a curl. Do you see between yesterday and today how these things developed? All vectors can be multiplied with a scalar. All vectors could be either dot product or cross product. Then what's the difference? Why don't I just call them dot products and cross products? The reason why is because the del operator operates in 3 dimensions. So when you look at your del operator, it actually is a 3-dimensional construct. Good? So gradient is important, divergence is important, and curl is important. So all of you that have taken E&M before, you guys, do you see Maxwell's equations developing? Literally from a very basic definition of what a vector does. So it's not fancy at all. It's just very simple. Flows exactly correctly. Okay, and all we've done between yesterday and today is go from 1D to 3D. That's it. And it all flows through. Okay, so now let me explain to you what a gradient is. So a gradient, when I think about a gradient, I think of it as a car going down a hill, right? So it's a positive gradient when we go up a hill, and it's a negative gradient when we go down a hill. The difference is, in this case, it is operating, the del operator is operating on a scalar term. An example of a scalar, temperature. Temperature is a scalar number, like, right? What's the temperature here versus what's the temperature up there versus what's the temperature outside? It's just a number. It doesn't have a direction. That won't make sense. Temperature having a direction, it won't make sense. So when that del operator operates on a scalar, it's called a gradient. Yeah, this one is going to be called a slope. And it can be positive, it can be negative, or it can be zero. But remember this, these are all going to be in 3 dimensions versus 1 dimension. That's the only difference. Okay, and then Griffith goes into the detail about stationary points and maximum points and all of that stuff. Divergence is fun. Let me explain what divergence is. What does the word divergence mean? How much something goes away is what divergence means. So a cross product in terms of divergence will be partial over partial x of E x del dot E equals partial E over partial x, partial y e y, and partial over partial z e z. And that implies how much E spreads.
Diverges.
Diverges. Yep. Woohoo. So a field that does this. Is this divergence positive or negative? Positive. Is this positive or negative? Negative?
Ooh,
And what about this one?
neutral.
0. And again, remember, this is going to be the dot product, right? Okay, now moving on to the curl. How do we write curl? So the way we're going to write curl is going to be exactly how we wrote it for A cross B. Partial over partial x, partial over partial y, partial over partial z, ex, ey, ez. Everybody's taken linear, right? So everybody knows matrices? So are we good? Excellent, thumbs up. And what does the curl mean? And I'll tell you how I think about it. I think about it if my vector field is doing this. Going around. So you know how I think about it? If you take a cap of a bottle and you put it in your field, that could be water flowing. And if it starts to not just necessarily rotate, but rotate about an axis, I call it that it is in the field that's curling. So if it starts to go like this, right, all around, then the curl is large. If it starts to twist about its axis immediately, it is in a field that curls. Got it?